let's deal with forces on an incline. Okay, so here's a ramp, and let's put a box on the ramp. A cart, box, whatever, doesn't matter. Any object on a ramp. Okay. Now there's two ways to go about doing this. There's an easy way and there's a hard way, and I'm all about doing things the easy way. But it doesn't matter which way you pick. The very first thing you got to do is label your forces. This is the force due to gravity. Gravity doesn't care that it's on a ramp. Gravity always pulls straight down. Okay, so gravity is always going to pull in this direction. The normal force is always there if there's a surface. Okay, and the normal force is called normal. Normal is another term for orthogonal or perpendicular or right angle or 90 degrees. Okay, the normal force is at a 90-degree angle to the surface that exerts it. Okay, this ramp is exerting the force, so the normal force is actually at an angle. Now this is an issue, right? We can only add vectors if they're in the same direction or in opposite directions. The normal force is pushing this way, gravity's pulling straight down, they're not in the same direction. I cannot add them together. Okay. Now the easy way to do this, as far as I'm concerned, is to say, okay, if I know this angle, I can deal with some stuff. Okay? And we'll look at that in a minute. Okay, there's the easy way then is to say, okay, here is actually components of gravity. The easy way is to actually reassign your x so it's not horizontal, it's so that its x is along the incline. Since all the motion's happening along an incline, this eliminates any acceleration in y. Okay, so we usually assign x and y like this, or you could go x up the incline, it doesn't really matter. Okay, and so then you have components of gravity. This is Fg y because it's in the y direction, and this is Fgx, and that makes your 90-degree angle right here. Okay, now using geometry I can show that this angle theta right here is this angle theta right here. So I'm going to redraw this triangle bigger. Okay, and so here it is. Here's Fg. Here's Fgy. Okay, and here is Fgx. This is a 90-degree angle. This is theta. Okay, usually you'll know this. Okay, and you'll want to be finding these sides. Okay, and we're going to use trig for that. Now remember, sine of the angle is equal to the opposite side over the hypotenuse, and the cosine of the angle is equal to the adjacent side over the hypotenuse. Okay, which means if I'm interested in Fgx, I'm interested in the opposite side of the angle, so I'm going to use sine. I can say that the sine of theta is equal to Fgx opposite over the hypotenuse, which is Fg, and if I solve that for Fgx, I have Fg sine theta equals Fgx. Okay. Similarly over here, if I want Fgy, I have cosine of theta equals Fgy over Fg, again multiplied by Fg, and Fg cosine theta equals Fgx. Okay, and so I've got these two components that I can deal with. Now I think this is the easy way, because then the motion's along the incline and I don't have to deal with anything, and I can say the net force in x is Fgx, okay, as long as there's no friction. I can say the net force in y is equal to the normal force plus Fg, which is actually equal to 0. Fg pulls the other way, alright, so the normal force is equal to the opposite of Fg, y, and so everything works out. You don't